Ever wonder how AI models like GPT-4 master language so quickly? It's not just about training on any data, it's about training on the right data. Today, we're unpacking FisherSFT, a revolutionary method that accelerates learning by selecting the most impactful information. Let's explore how it works. Here's the challenge. Training large language models requires massive datasets, billions of text samples. But not all data is equal. Some examples are redundant, some are noisy, and many don't actually help the model improve. Think of it like trying to learn a language by reading every book ever written. Sure, you'd absorb a lot, but you'd also waste time on repeats and irrelevant details. Traditional fine-tuning methods, like LoRA or adapters, focus on modifying the model itself. FisherSFT takes a different route. It changes what the model learns. Imagine teaching a student not by handing them every textbook, but by curating a highlight reel of the most transformative lessons. The secret: information gain, a statistical measure of how much new data reduces uncertainty. FisherSFT uses this to identify training examples that deliver the biggest aha moments for the model. It's like a GPS that highlights the most critical roads to your destination, skipping unnecessary detours. How does it work? The algorithm analyzes the Hessian matrix, a mathematical tool that measures how sensitive the model's predictions are to individual data points. Think of it as a sensitivity meter. If a single example drastically shifts the model's output, it's a high-priority candidate. FisherSFT approximates this matrix efficiently, focusing on examples that create the most significant ripples in learning. Picture solving a jigsaw puzzle. Some pieces fit perfectly, revealing the big picture, while others are duplicates or irrelevant. FisherSFT acts like a puzzle expert, instantly spotting the key pieces, so you finish faster without missing critical details. The magic happens through a greedy algorithm. At each step, it selects the example that maximizes information gain. But here's the twist: it doesn't guess. It uses multinomial logistic regression to approximate the Hessian, balancing computational efficiency with precision. This approach ensures the model learns from the most informative data, avoiding noise and redundancy. Let's get technical. The model's loss function measures how well it predicts outcomes, like guessing the next word in a sentence. The gradient tells it how to adjust parameters to reduce this loss, acting like a compass pointing toward improvement. But gradients alone aren't enough. The Hessian, a matrix tracking how gradients change with parameters, reveals the terrain's curvature. In FisherSFT, the Hessian has a special structure: a diagonal matrix showing individual feature importance, plus a rank 1 matrix capturing global trends. This design ensures stability, preventing the model from overfitting to noise or getting stuck in local minima. The paper proves error bounds, mathematical guarantees that the model stays on track even with imperfect data. It's like a safety net. FisherSFT balances information gain and parameter updates, achieving state-of-the-art efficiency. By training on fewer examples, it matches or exceeds traditional methods while reducing computational costs. So next time you see an AI that's super smart but trained on limited data, remember, it's not magic. It's math, clever, elegant, and built to navigate the complexities of machine learning. Thanks for watching. Stay curious, and we'll dive deeper into the numbers behind the magic next time.